Hi everyone, a very short video to tell you a bit about the progress that I made on the Voxel engine. Maybe you remember in the previous video, I told you that I was going to work on the two generation and the chunk system, but I didn't. I worked on physics instead because to me there's two issues with this project. The first one was rendering. So I think this is solved since the last video. I can have like any kind of voxel size that can be in their own container if I want. Like they have different voxel size, they're in different containers. Like everything works fine. And like I can modify, I can edit, and I can do whatever I want in any container. So the only problem that was there to me was like physics. I wasn't sure that I could do it because I wanted a good physics engine to work with any kind of voxel size. These voxels are already very small, so getting a good physics engine with that was really hard for me. And so during those 2, maybe 3 months, I tried many different techniques, especially during Christmas. Like that was crazy. And I could make like a 10-hour video at least about the different methods I used. But to make it short, I'll go directly to the results. So for the solver, I'm using the augmented vertex block descent, which is a new technique from last year that is known for being very, very stable. And this is true. Like once you find the nice parameters, it's completely awesome. You can make like big towers, etc. Like that's just an awesome algorithm, honestly. And yeah, the only problem of this algorithm, and maybe it can help someone trying to re-implement it, is that finding the good set of parameters is very hard. And like sometimes you will think that you made an error while implementing it, but it's just that you don't have the right parameters, and so the outcome of the physics engine is completely crazy, while your implementation is completely fine. So it's just a matter of parameters, which is a bit sad to me. It's the only issue of this algorithm, but else it's absolutely terrific once you have it working. And so the second thing for collision detection, and this is where I spent most of my time because this was solved fairly quickly, was the collision detection. I've seen that in teardown, they are looking at each voxels on the surface, and based on a classification, like is it a vertex, is it an edge, is it a face, they do computations. But like this wouldn't scale well with the idea that I have many voxels. So I tried a lot of techniques, and at some point I got an idea. I will tell you a bit about it in a few minutes. But yeah, this is just to show, like with teardown, I think that this would be kind of hard to make work in an engine where you are checking each voxels. But yeah, so the idea of my technique is that after trying different methods, I noticed that what I'm interested in is only some points, and those points are like the same from the perspective of the two objects that they are in contact. So the idea is that I'll take this example. I start from the center of mass, and each frame, like you have some probes that are moving inside of the mammoth. So like the probe is moving, and it's bouncing inside of the mammoth as if like it was completely inside. So based on this, it bounces. And also there's a magnet effect. So this magnet effect depends on the value that I set. It's an hyperparameter that will define how magnetic it is to the other object. So the probes that are, for example, in this world, they are moving. Like the probe of this mammoth is moving toward the ear, and when they coincide, like not really, like not when they collide, but when they have a small radius between them, boom, it means you have a contact. So it's a bit more complicated, and maybe I should do a big video about it. But the idea is there, and this is how I can like do the collision detection of such a big thing in real time at more than 100 of FPS. The cool thing is that it works with any voxel size. Like I can have, you can see like a ball here. It will work completely fine. And with AVBD, like the augmented vertex block descent, it can give like some very cool effects. Boom. Yeah, I'm already seeing like pirates boats fighting with cannonball. I don't know why. I'm pretty sure it will be fun. And it's also quite performant. So for now, everything runs on a single thread because mainly because I didn't implement the multi-thread, but it could work completely with multi-threading. First, because the augmented vertex block descent is friendly with periodization. I could even go on the GPU, and my collision detection algorithm with the probes, I could move them maybe with a compute shader or in different threads on the CPU. For now, I will keep it on the CPU because except if you have more than 100 of cubes, I don't see a reason for this. Like 100 of objects, not cubes. I don't see a reason to parallelize it yet. Maybe in the future, but I don't want to spend time optimizing stuff for some specific use cases. It's already pretty good with like this. Cool. Yeah, so maybe the final thing that you would like to see is the inertia. Maybe you need to notice it. So the inertia and everything is calculated on the fly through a hierarchical structure. So, oop, oop, like you can see, the inertia is the same. It's calculated based on the shape, the mass center, etc., and the amount of voxels. Each voxels have a density, like the. So for now they all have the same, but no, I think the green one it is a little bit bigger. So we'll, can I reduce? No, yeah, never mind. Maybe if I do this, oop, there. So the green one is a lot more heavy. So you can see that if I let it pour, it should, yeah, have a different behavior than if it was just full of the same voxel. But the idea is here, and it just depends on the shape that you want. So, oop, if I do this, yeah, you see, like it moves exactly as you expect it. And one test that I like to do is just throwing this inside of the tree, and boom, like everything's fine. It just finds a stable position right here. There's so many optimizations I could do because I'm not sleeping them quickly enough. Like they stay at least for 10 seconds without sleeping. So many things I should optimize. Uh, but let's see that later. And yeah, maybe I can show you a nasty, very nasty configuration. Like boom, with for the probes. Like so for the probes here, it's a real nightmare, especially for the probes of the real world. And yeah, you can see that you will see that it is still able to work pretty well. Whoop. Where's the ball? Yeah, I like this ball. Whoop. Oh, it bounced on some of this. 4-4. Cool, no? I really enjoy seeing this kind of behavior. Oh, and even with the mammoth. So I think, yeah, maybe people will be able to play football or different kind of sports inside of uh, this world thanks to this engine. Oop. Yeah, the inertia makes it fall. Oop, fall like this. Yes. So yeah, that's mainly what I wanted to show you. I hope you liked it. And in the next video, like my next focus, this time it's for real. I will focus on getting a good interface to edit and modify stuff because yeah, like I'm modifying stuff with this. It's really not easy to use. I would like to be able to select stuff, copy, paste, etc. Like this is the next focus because my goal is maybe for you to have a first version to try in let's say 2-3 months, maybe 6 maximum. But let's see that later. So thank you, and see you next time. Bye.